let's take a brief look at some other quantum algorithms designed to show the power of quantum computing. The Dutch Jozsa problem, published in 1992, is formulated like this. We have a black box oracle function which maps n bits to 1 bit. And we know for sure from a reliable source that this function is either a constant or balanced. A balanced function is such function that returns equal amounts of ones and zeros. So the question is the same as in Deutsch's problem. Which case of these do we have? Is this oracle function a constant, or it is a balanced function? Now, if we don't need 100% certainty, then classically this problem is not extremely hard, because if we call this oracle, for example, 10 times with random inputs, and each time we have the same value, then we can bet that it is a constant, and the probability of mistake would be this. But if we need 100% certainty, then a constant in a black box becomes a nightmare, because we have to check this number of inputs to be sure that this function is constant. But for the quantum case, the things are much brighter. To solve this problem, we will need almost exactly the same circuit scheme as in Deutsch's case, except for one thing. We now have n qubits in the X register here, and we have to apply the n qubit Hadamard transforms here and here. So let's do it. We have this state, and we apply n plus 1 qubit Hadamard transform, which gives us n plus 1 divided by 2 here. And remember this formula that we proved on the previous, that you proved on the previous week for the Hadamard transform, time to use it, and we do. X from 0 to n minus 1, x, and 1 transforms to this. Okay, now it's time to apply our quantum oracle, and on the states like this, you remember how it acts on the states with Hadamard minus in the last qubit. So again, we have this and the sum over all vectors of the space. And now minus 1 f of x, and this minus vector here. And we are now going to take a close look at this state here, which we have to apply Hadamard transform to. So let us concentrate on this X register now, because only it we have to modify and measure from this point. So we can forget about this and about this. Now imagine that the function f of x is a constant. Then this minus 1 is going to be always in the same power, and we can put it out of the sum here. And the sum transforms to something like this. and -1 here in this function value. Now this sum is very familiar to us. We just have seen it on the previous slide. This is just Adamar n qubit Adamar of n zeros vector. Or we can write it like this. So after Adamar and measurement, we will get this vector, which consists of all zeros, of n zeros. Okay, now if function f is not a constant, now it is balanced, then we have two types of coefficients here in this sum. And we can split this sum like this. So by the value of the function. And since this -1 here, if the function f is 1 equals to -1, we have to put this minus here. And of course, the coefficient here. Now let us recall the formula for the Adamar transform. This is our formula for Adamar transform. Now imagine this vector y is all zeros. Then this thick point product here is 0. And this vector is always with a coefficient +1. So for any vector x, if we apply Adamar transform to it, it will be the sum of all basis vectors of the space, but this vector with zeros will be always with a coefficient +1. And we have the equal amounts of terms in this and this sum, because the function is balanced. And we remember that these sets have the same number of elements. So here we will have this number of these vectors of all zeros, and here we will have the same number of these vectors, but with minus. And these vectors will self-destruct. And in the output, there will be no vector of all zeros. And if we measure the result, we will obtain any other vector except this one. So only after one application query to the quantum oracle, we can distinguish balanced and constant functions, because for constant function, for a constant function, we get exactly this vector as a measurement result, and for a balanced function, we don't. We get any other vector. And this self-destruction of vectors here reminds me of interference. It is an interference. Bernstein-Lazerani problem, 1993. Again, a function maps n bits to 1 bit, and we know that the function is implemented like this. So it's like a dot product in Z2. Well, we know this much, but we don't know this number A, and we want to know it. And again, the function sits in a black box, so we can't look inside. We can just query this oracle, feed it some inputs, and see the outputs. And classically, the problem is not that hard. We can feed the inputs like this with ones in only one place to obtain different bits of this A. So since A is n bit, we will need n oracle queries in the classical case. But we already got used to solve the problems in just one oracle query. So we proceed to the quantum case, and the quantum algorithm is the same as for Deutsch-Jozsa problem. And since it is the same, it acts the same. So up to this point here, we have the same value in the input and in the all registers in the system state. But the function f here is a thick point x. And if you look at this expression here, you may notice that it is exactly Hadamard transform of A. So after this Hadamard transform, and as a result of measurement, we will get the value of A in just one oracle query.